All right, hi guys. We're looking at our next topic, which is about perfect squares and perfect square roots. So let's talk for a second. When we're looking at perfect squares, we need to know what is an exponent. So specifically, what is an exponent? That is a way to show repeated multiplication. So for example, let me scroll back over here. All right, so for example, you could have 2 with a little exponent of 2 up there, which means the same thing as 2 times 2, which would equal a 4. Or sometimes you might have it with a variable such as x to the third, maybe. We've seen these in the past, which again is just a short way to express x times x times x. Again, that exponent tells you how many times that object is there with multiplication. So let's see what happens when we bring in some numbers, and you've seen these values before. Let's check out the first one, 5 squared, which is the same as 5 times 5, which is 25. And then if I try the next one, 10 squared, that's the same as 10 times 10, or 100. Let's try some more. 7 squared is the same as 7 times 7, for 49. And then maybe one that we're not quite so familiar with, 14 squared, which is the same as 14 times 14. Sorry, for 196. So again, that's dealing with your exponents. Now, to undo these exponents, the opposite of the exponent of 2, the squared, is the square root. But more specifically, we call that a radical sign. That symbol is called the radical. And when you square root something, that means there is an understood invisible 2 in that tiny little space, because we're wanting what's called the second root. So it's the reverse of the squared. We're trying to find out whatever is inside that radical sign, what number taken to the second power would give you that value. But again, since the 2 is understood, it's not there. In Algebra 2, you will see that sometimes you have a cubed root. There'd be a 3 there, maybe a 4 or another number, maybe a half even. But let's talk specifically about what is that radical sign. So specifically, it is a way to find the number multiplied by itself go back to the other side here, to find the inner value. And so today we're going to be looking at what we call perfect squares, meaning that there is one number that we can use, and we're sticking to positives right now. One number times itself, that'll give you exactly what's in that value inside the radical. So if I was to look at possibly some examples, whoops, where's my example? So if I had an example like the square root of 9, well, that would be a positive 3 or maybe a negative 3. because positive 3 times positive 3 is still positive 9. And same idea for the negative. Negative 3 times negative 3 is still positive 9. But for right now, we're going to be just sticking to the positive version of those values. So let's see what happens. And there's some things we can do to figure out some of these square roots if you don't recognize them right away. All right, so first things first, we're going to use the factor tree. And I'm going to zoom in here on this to break down the values. And what we're looking for are either breaking them down to either prime numbers or pairs. And we'll talk about that in just a second. So let's do that with our next example here. Example 1. So right now I have square root of 9. So I'm going to break that down into two factors. Again, factors are just two things you multiply. Two things that I know I can multiply together and get 9. And we want to use a number other than 1 and itself. So in this case, I know I can do 3 times 3. Now, right now we have a pair of 3s. And that's what we're trying to find when we break down any value inside the square root. We're looking for pairs of numbers. So once I find a pair of numbers, that takes us to the next step. Once you find a pair, you bring out a single number of that pair. So I'm going to bring out, because I have a pair of 3s, again, because I have a pair, 2, I can bring just a 3 outside to that equal sign. And that's what we're looking for, just pairs. So let's try another one. And so the square root of 9 would be the 3. That is my final, because there's nothing else to break down below those 3s. Let's try another one, 121. The only numbers I can use to multiply together and get 121, besides 1 and itself, is 11 times 11. And again, there's another pair. So I only need to bring out a single 11. And there's nothing else I need to break down at the ends of those branches. And that's why it's called the factor tree, because those pieces branching off from the 121, those are the branches of my factor tree. Now, let's try some more. Now we're looking at square root of 64. All right, so one thing I know, yes, we can do 8 times 8, and there's my pair. But what if you don't recognize that immediately 8 times 8? All right, I do know that I can do 2 times 32, and I get 64. Now, the 2 there is a prime number, so I will leave it alone. But 32 can go farther. 32, I can do 2 times 16, and I don't need that 32 anymore. Now I have a pair. Sorry, that's way too big. Right now I have a pair of 2s at the end of branches. They do not have to be at the same branch. So that means right now I can bring out 1, 2. My 16 can go farther. Now, if you can recognize that the same number times itself will give you any of these pieces, that's what you want to try to use. So example, 4 times 4 will give me 16. But if you don't recognize that right away, that's fine. You could still take it farther. But because I know 4 times 4 will give me 16, there's my pair. I don't have to go any farther. I can bring that 4 outside now. And this is our next step. If we have more than one value on that outside, we multiply any values back together. If there are some left outside, actually, let's see, multiply the values back together if there are more than one on the outside. We'll leave it at that. And so that gives me my final answer once I multiply the two of those together, which is my 8. Now again, at square root of 64, if you know that 8 times 8 is square root of 64, then that would be my pair as well. Whoops, sorry, way too large. Meaning that if I have square root of 64, and I know right away I can do a pair of 8s to get that, there is my answer in that one step. But again, if you don't remember 8 and 8 make 64 when multiplied, just break it down in the way you know. Now with division, you can find those individual factors. If you're not sure what your factors are, you could take your, in this case, 64 and divide by 2 to see if it will divide into it. In this case, it gives me 32. If you don't know, can't think of two numbers that multiply to be 32, try dividing that by 2 and see what the other factor is, and keep breaking it down. Let's try 81. Okay, one thing I know is I can do 3 times 27. And again, that's if you don't recognize right away that you can do 9 times 9. 27 can go farther down to 3 times 9. And again, there's a pair. Again, they don't have to be at the same level. So that means I can bring a 3 out. 9 can go farther to another 3 times 3. There's my pair. So I can bring another 3 out. Multiply the leftovers back together. 9 is my final. All right, let's try some bigger ones. All right, so now we're looking at the square root of 256. All right, and one thing I know about square root of 256, again, you could start with 2. 256 divided by 2, that'll give you your other factor. I'm going to try something a little bigger. I know 256, if I divide that by 8, I can get 32. And then I can break both of these sides down. My 8 can go down to a 2 and a 4. My 4 can go farther down to a 2 and a 2. And right now, there's a pair. So that means I can bring a 2 out. Now, again, because I broke down the 8, I can't use it anymore. And because we broke down that 4, I can't use it anymore. Now let's bring down 32. 32, I could do 2 and 16. And there's a pair of 2s, even though they're on 2 separate branches, that's fine. Again, as long as they're at the end of one of these pieces, they can pair up. So there's another 2 I can bring out. Let's keep going. 16 can go farther. Oh, I know 16 is 4 and 4. There's a pair there at the end. 16 is done. I can bring out now the 4. All right, and then let's, even though we have 3 this time, still multiply them back together. 2 times 2 is 4. So this part is 4. We multiply by that remaining 4. And 16 is my final. Let's try another one. All right, now we're looking at 324. All right. So let's say all you know is it's divisible by 2 because it's even. That's fine. I can do 2 and 162 to get 364. So the 2 is done. 162 can go farther. And again, maybe you only know it's divisible by 2 because it's an even number. Well, I can do 2 times 81. And right now, there's a pair. That 2 can come out to the equal. And 81, I know, is 9 times 9. There's a pair. So then I can bring the 9 out. Last rule, multiply those leftovers back together. 18 is my final. Okay, guys, I think that's all of them that we've done. Yes, it is. So I hope you enjoyed learning a little bit about how we deal with your perfect squares and your perfect exponents, your square exponents. All right, so please don't hesitate to reach out to me at all if you have any questions. Bye, guys.